talk about that. Hey, here we go. We're going to talk about what's hot, enthalpy. All right, thermodynamics. Okay. Have you heard about this? The first law of thermodynamics. People. No, I don't. I don't have the Simpsons clip. When you go to college parties and people want to talk really smart, they start talking about the law of thermodynamics. The laws of thermodynamics. There are 3 of them, and so you can quote them. They're really not that smart. Okay. The first law of thermodynamics basically says something that I'm sure you guys have heard before. Energy can't be created, and it can't be destroyed. Okay. There's a law of conservation of energy, basically, is what it is. In other words, the total amount of energy in the universe is constant. If you really want to cause somebody's mind to blow, here's the deal. You know when the Big Bang happened? Okay, you know the story of the theory, I shouldn't say story, the theory of the creation of the universe. The amount of energy that existed 1/10 of a nanosecond after the Big Bang is the same as the amount of energy that's in the universe right now. Okay, that just blows your mind, right? Okay, only the universe now is much, much, much bigger than it was way back then. Right? At the very moment of that Big Bang, the universe was thought to be an extremely tiny, infinitesimally small pinpoint. So all that energy was crammed in that tiny little spot. And now all that energy is spread out. So ultimately what that means for us in chemistry, we'll make this more macroscopic now, is that every time we do a chemical reaction that releases energy, that energy is getting released from somewhere. It's getting released from chemical bonds. Chemical bonds can get broken down and turned into energy. Okay. Or if we're doing a chemical reaction where energy is being absorbed, that energy is actually going into creating chemical bonds. Okay, so you can go one way, you can go the other way. And the way the slide says it, if the system loses energy, it must be gained by the surroundings. That would be an exothermic reaction. That would be like a firecracker. Right? And if you're watching this video later, man, today is a cold day. Lots of people have bad noses. All right. So the way we measure and talk about this energy that's given off by reactions is talking about an idea called enthalpy. Okay? Enthalpy is used to quantify, to give us a number for heat flow into or out of a system in a process that occurs at constant pressure. The reason why we've got to have that phrase in there is because if the pressure changes, the enthalpy changes. So we try and measure enthalpy of reactions in situations where we can maintain the temperature, maintain the pressure. It's an extensive property, meaning that the amount of stuff will matter. The amount of stuff will determine how much energy is given off or is absorbed by the reaction. And that kind of makes sense, right? If you want a lot of energy, you need a really big firecracker. If you want only a little bit of energy, you just need one of those tiny little ones. What do they call those? Snap pops. Right. The ones you throw at the ground, a tiny amount of energy, right? If I made a snap pop the size of your head, you'd expect a lot more energy. Yeah, you might get some more fun out of that. A snap. Okay. So usually measuring enthalpy is a process where we don't measure the actual enthalpy of the system, because if you measure the enthalpy of the system, you need to know all of the energy in the bonds, as well as the energy due to heat, as well as the energy due to nuclear, any energy that's in the system at all. So usually we measure enthalpy as a change in enthalpy, as delta H. Okay. So delta H is going to be our term that is used to talk about heat that's given off or absorbed during a reaction, and that could be a physical or a chemical reaction. We could just be dissolving something, in a physical reaction, or we could actually be combining two chemicals. And there is some meaning from this. Somebody asked me at the beginning of class, if you could tell whether something was endothermic or exothermic simply by looking at the chemical reaction. Here's how you tell. A positive delta H tells you that the system is absorbing energy. Think about that for a second. A positive means it's absorbing. Does that make sense to you guys? Okay. So that means that it's an endothermic reaction. It's absorbing that energy. A negative delta H means that the system is losing energy. That means it's exothermic. Now let's think about this in slightly different terms. Which one is hotter, endothermic or exothermic? Which one feels hotter? All right. Think about it this way. The system is the chemicals that are doing the reaction. You are the surroundings. Which one feels like it's giving off, right? Exo. Okay, so you might want to add something to your notes here that it looks like exothermic, a negative delta H is hot. Endothermic, a positive delta H would feel cold. Okay, so the delta H, does that sign make sense with temperature? If you think about it, eventually does, but when you just take a glance at it, it doesn't. Okay, so it's kind of counterintuitive the way it's written. I think this is the same visual your book uses. Notice it's showing that the system is taking heat in from the surroundings, right? Okay, it's just a visual. It's showing you that delta H is going to be greater than 0. So this is where delta H is going to be a positive number, endothermic. All that stuff says exactly what I just said. Okay, and this is where the system, the chemicals, are releasing that heat. Delta H is now less than 0, so that means that delta H would be negative, and it's releasing that energy into the surroundings, which means that we got an exothermic situation. I think that's just a visual way of describing the same thing on the last slide, right? Okay. So, as Emily just said, this is going to be an exothermic reaction because this reaction is losing energy to its surroundings. The system is losing energy to its surroundings. So if we were to make a graph of energy versus time, because we do this sort of thing in chemistry. Okay. I know. Okay. So we're trying to apply more math skills to chemistry. This is good stuff. We draw that line representing the before, and then, if I could find my gosh darn cursor again. There it is. Gosh darn. Can't swear I'm recording this. Whoops. This is my after. I can't even say profanities because that's a bad word. Oh, shoot, I just said it. All right. So we've got the before and we've got the after. Okay. Notice, why is it that I put after lower than before? It lost energy, right? Okay, over time it lost energy. How do I know that? It's exothermic. Okay. The system, the chemicals lost energy. According to this graph, that's what's happening. And according to the definition of exothermic, that's what happens. What do you think an endothermic reaction is going to look like? Okay, all right. So let's see if we're right about that, because the next example is endothermic. Okay, so check this out. We've got a positive delta H. Positive delta H means endothermic. And that means that the system would be absorbing energy or gaining energy. Okay. So this is what we call thermostoich, guys. We get a balanced chemical reaction that includes the enthalpy information. Okay. And we get a question. Let me point something out to you guys. What this reaction is telling me is that if I use completely 2 moles of SO2, I am going to get produced 99.1 kilojoules of energy. I'm saying produced because this is releasing energy, right? It's exothermic. Another fact I can glean, in this case we do use kilojoules because the reaction shows kilojoules. Joules are so tiny that we usually use kilojoules. Okay. Another fact I can glean from this is that if I were to use up completely 1 mole of oxygen doing this reaction, I would get a release of 99.1 kilojoules of energy. Or I could glean a third fact from this written reaction. I could glean from here that 2 moles of sulfur trioxide being made would also produce 99.1 kilojoules of energy with it. Okay, so do you guys see that I'm getting some mole to energy ratios? And I get the same, I get 3 mole to energy ratios here because I've got 3 substances. If I had 4 substances, I could get 4 mole to energy ratios. Okay. So if they say to calculate the heat given off, when 74.6 grams of SO2 is converted to SO3, I'm simply going to do this as easily as I can. 74.6 grams of SO2. This was all in moles, right? So the first thing I need to do is I need to convert my grams of SO2 into moles. Okay, moles of SO2. Oh shoot, I can't do this. Grams of SO2 on the bottom, moles of SO2 on the top. I said shoot. I can go back and show you the recording. 1 mole of SO2. How much does this weigh, guys? Is it 64? 64.06 is what I'm being told. Are we going to agree with that? Okay, 64.06 grams. All right, is 1 mole. That means grams of sulfur dioxide and grams of sulfur dioxide go away. Here's the easiest thing to do, guys. Check this out. I need to write moles of SO2 on the bottom, right? I can convert moles of SO2 to energy, can't I? That's one of the ratios that's available up here. I can talk about 2 moles of SO2 making 99.1 kilojoules of energy. So I can just say 99.1 kilojoules of energy on top. And how many moles of SO2? Okay, I'll put negative. How many moles of SO2? 2. Okay. I do the math. 74.6 divided by 64.06 times negative 99.1 divided by 2. So, yes, to add to the recording here, I did make a slight mistake. When I doubled everything to start out with, so we wouldn't have fractions, I should have doubled the energy too. So all these ratios are related to 198.2. 198.2. That means that the answer should be 115 kilojoules. And those of you guys keeping track of the sign are going to be telling me it's negative 115 kilojoules, according here. So the question is, what does that negative sign mean on negative 115 kilojoules? It just means that energy is being given away from the system. All right. So you can answer that there's 115 kilojoules given away from the system, or you can just answer that there's negative 115 kilojoules. Both should be understood as correct answers.